polytopes are made out of the regular polytopes 1 dimension lower. In the same way that we made platonic solids out of 2D regular polygons, we can now try to make 4-dimensional regular polytopes out of 3-dimensional platonic solids. Each one of these 4-dimensional regular polytopes is of an object that has as a surface a thick crust of 3-dimensional platonic solids. And just like we made a cube out of squares, we're now trying to make a hypercube out of cubes in its surface. We used to take 3 squares and then forcefully try to close this gap of 90 degrees, and by closing it we force this corner to pop out of 2 dimension, become a 3-dimensional valid polyhedral corner, and that's the corner of a cube. Now we're doing exactly the same thing, except think that behind each one of these squares there is a complete cube, and these 3 cubes now are sharing a joint edge perpendicular to this plane in that particular corner. So there's a 90-degree wedge of open space, and we're trying to forcefully close that, and we cannot close that in 3 dimensions if there are cubes behind each one of these 4 visible squares. But trust me, if we really do that and we can pop out in the 4th dimension, we can close up, these cubes, and we get a hypercube.
Those cubes behind these that I was being asked to imagine, they've kind of overlapped with each other now.
No, because they pop out into 4-dimensional space in the same way that when we took these 2-dimensional squares and we forced them to close, they didn't overlap. They just popped out of 2 dimensions into 3 dimensions. And 4-dimensional space is really much bigger than 3-dimensional space, so there's ample room for these cubes to simply pop out and form a true 4-dimensional corner.
But to my 3-dimensional eyes, here sitting in 3D space, I'm like, how did that happen? But if I had 4-dimensional eyes, I'd be thinking, oh, that was...
That's correct, and now you're hitting on the real problem. And so we can figure out that this must be possible, but then can we visualize that? I mean, how would you know what this thing looks like? Well, for that we have to use some kind of a shadow or a projection of a 4-dimensional object down into 3-dimensional space. And I'm sort of torn between, should we use a shadow or should we use what I would call a wireframe? And you see the trade-off between those 2 options. Just like if I show you the wireframe of the dodecahedron, you can really see through it, and it tells you much more than if you just had a faceless shadow of this object. You can eventually start to get a feeling by looking at 3-dimensional wireframes or projection of such wireframes what the 4-dimensional object might indeed look like. In doing this projection, we still have an option. We can project in various different ways. We're going from a 2-dimensional square to a 3-dimensional object, and in an oblique projection I start with the red square in front, and then the blue square is the ones in the back, and the green lines essentially show me the depth. We can do the same thing by starting with a complete cube. The red cube is in front, the blue cube is in the back, and then the green lines show essentially extrusion of this cube in this oblique direction. Alternatively, we can use a perspective projection. Everything in the back would appear smaller, and we can look straight at the face, and by doing that, the back face will be a smaller square, so really behind the red square, and the green lines show kind of the depth going from the front to the back. And the same we can do with the complete cube, and we get in the back a smaller cube shown in blue, and then the edges that go from the front to the back are shown in green. So here is the oblique projection. You can see the fatter cube being sort of the one in front, and then the thinner cube in the back, and then the slightly conical edges leading from the front to the back. So that's a valid depiction of a wireframe of a hypercube. And here is the alternative model, a perspective projection. So the bluish cube is the front cube, and the yellow cube is the one in the back, which is here much smaller. The red edges that go from the front to the back. And this hypercube has a total of 8 cubes. The front cube in blue, the back cube in yellow, and then some squashed cubes here showing 1 on each of 6 faces. So there's a total of 8 cubes making the surface or the thick crust of the hypercube.
So that yellow cube isn't inside the blue cube?
No, in 4 dimensions it would be sort of up in the 4th dimension a certain distance, because of perspective projection. What's further up there, gets projected into the back and appears smaller in this projection. Now we're going to systematically look at all the platonic solids, see how many we can group around the shared edge, how much empty space there is, and then we push that one